Hi guys, my name's Andy. We're going to be talking about the fate of lactate and this week's CAP. So let's get started. So we're going to start off with the differences between lactate and lactic acid. Lactic acid is actually an organic compound that is formed through anaerobic glycolysis and actually dissociates quickly into the body to free up hydrogen ions. And during this dissociation, lactate actually is formed as the remaining compounds binds to another sodium or potassium ion to actually create lactate. So lactate's actually that burning sensation more than it is lactic acid, as the majority of lactic acid dissociates and presents as lactate. And this burning sensation is actually a feedback mechanism our body uses to prevent further damage, tissue damage under extreme physical conditions. So now we're going to talk about the Cori cycle, in which its main function is to remove lactate from active skeletal muscle and convert it back into glucose via gluconeogenesis in the liver. And it's ultimately going to restore glycogen stores after being depleted from physical activity. We're going to start off talking about glycolysis first, as glucose is converted into pyruvate, and it can either go aerobically into the Krebs cycle or anaerobically into the Cori cycle. For this case, we're going to talk about the Cori cycle. It's going to start with pyruvate or glucose breaking down into pyruvate, and here it's going to combine with lactate dehydrogenase, or not combine, but be assisted by lactate dehydrogenase to convert into lactate, which is then transported to the liver via the blood. And the lactate is going to be converted into pyruvate with the assistance of lactate dehydrogenase once again, and then it's going to convert back into glucose. Now this glucose is going to transport back into the bloodstream to either maintain blood glucose levels or go back into the skeletal muscle and replenish glycogen stores. During light to moderate activity, which is defined as below 50% of your aerobic capacity, our bodies are able to achieve a stable level of lactic turnover, which is defined as the rate of lactate formation is equal to the rate of lactate disappearance. Via the oxygen consuming reactions are meeting these demands, but as intensity increases, we're going to have a larger oxygen deficit because it requires more oxygen to oxidize lactate at higher intensities. So in untrained individuals, lactate is going to start accumulating at about 50 to 55% of our aerobic capacity, while in trained individuals it's going to increase up to 80 to 90%. And these increases are due to training adaptations from endurance training that will increase capillary density, increase mitochondrial number, so that produces a better capacity to produce ATP, therefore leading to delaying lactate accumulation and also enhancing performance. And also, if you implement resistance training as a supplement to endurance training, it also delays the onset of blood lactate accumulation and lactic threshold, which we will talk about later. So how do we use lactate metabolically? Lactate is actually a valuable source of chemical energy that can be used for quick bursts of energy in low oxidative situations or anaerobic situations. And it's been, as stated before, it's been used in the Cori cycle. And another case is for lactic shuttling, in which lactate produced from fast switch fibers can circulate to other fibers that help ultimately convert back to pyruvate to be used in aerobic metabolism to help supply more ATP production. And it's also a precursor to synthesize carbs via the Cori cycle to aid in the replenishment of glycogen or glucose. So now we're going to talk about lactate accumulation, and as stated before, lactate does accumulate at higher intensities of exercise due to the low lactate turnover, because we're not getting an adequate enough of oxygen to meet these demands. And the two notable points on this graph here are the lactic threshold and the point of onset of blood lactate accumulation. These 2 points are sometimes mistakenly interchangeable with each other, but that's not really the case as they represent different points. The point of lactic threshold is defined as the max aerobic capacity someone can reach before their blood lactate increases by 1 millimole, while OBLA is described as a 4 millimole increase in blood lactate. And researchers use OBLA as a better predictor of endurance performance compared to VO2 max, because we don't perform endurance activities at our VO2 max, and rather it's more of a steady rate of exercise. And OBLA is actually represented as the max level of steady rate exercise before changing intensities, as we see that this point of OBLA is going to increase ventilation up here at a higher and higher incline, and ultimately it's going to also increase lactate, because we're not getting enough oxygen to oxidize the lactate, and ultimately leads to cessation of exercise, or before that, fatigue actually, and then cessation of exercise. OBLA is also influenced by the type of activity being performed, the muscle fiber types being activated, mitochondrial number, capillary density, and enzyme concentrations. The last thing we're going to talk about today is buffering, and buffering is defined as the reactions that minimize change in hydrogen concentration. So this is one way our body is able to regulate pH levels. Normally we are at a 7.4 pH level. In this case, we're going to be talking about sodium bicarbonate, as it buffers lactic acid. And when it buffers lactic acid, it forms a carbonic acid and sodium lactate. Buffering reactions are dictated by hydrogen concentration, so in either cases of acidosis or alkalosis. In acidosis, we're going to have increased levels of hydrogen concentration, so that stimulates our body to increase ventilation to remove excess carbon dioxide. But in alkalosis, we're going to be a little bit more basic in our body. We're going to have decreased hydrogen concentrations, so we're going to have to inhibit ventilation to retain all of our carbon dioxide to increase our acidity. As exercise intensity increases, though, the demand for buffering also increases, and making it harder to regulate our pH levels. So one might hit lactic acidosis, which is when our body becomes acidic due to the lactate accumulation, because we have an increased amount of NADH concentration, so that's going to convert pyruvate into lactate, and lowering our pH levels. And when our pH levels get to a point of 6.4 to 6.6, certain enzymes in our body aren't able to function properly, so that's going to limit our ATP production and ultimately lead to fatigue and cessation of exercise. The burning sensation, as mentioned before, is because of this changed pH level, and in which, see here on this chart, that as maximum exercise increases or intensity increases, we see that our blood lactate starts rising up, as well as our blood pH is starting to decrease, becoming more acidic. And also in here we can see that as the more lactate we have in our blood, or as it increases, our pH levels are going to start decreasing and produce that burning effect to signal our body to cease exercise so we can recover. So here are my references. I just hope you guys learned something from this, and let me know if you have any questions. Thank you.